Okay, we are on to the ADC question, and I'm going to start with this one by just kind of walking through what's going on in the registers up here and looking through the problem details, because it's going to ask us a bunch of questions about what's going on with the analog to digital converter, and we need to look at some of these details first to know what's going on here. So I'm just going to start with ADCC GFR or CFGR and kind of walk through the bits and see what might matter. So bit 31, JQDIS, injected Q disable. We have not heard about that, so it's not likely something we care about. But let's go ahead and look at what the bits mean. It does say that 0 is injected Q enabled, but it does say in the note that it only writes that bit when AD start is 0 and JAD start is 0. So it looks like something that we'd have to sort of configure elsewhere for this to matter. So we'll just ignore that. The next set of 4 bits, or 5 bits from 36 down to 26, is AWD1CH. These are set and cleared by software. Select the input channel to be guarded by the analog watchdog. Again, not something we've really talked about, so probably not something we're going to ask you about on the exam. We can also assume that those don't matter here. Automatic injected group conversion, not something we've looked at. Let's go continue on. Analog 1 watchdog, again, nothing. Analog watchdog. Enable watchdog, JSQRQ mode, not a thing we've talked about. Discontinuous mode, nope. Continuing on here. Discontinuous mode channel count, nothing set, so we can ignore that as well. Discontinuous mode for regular channels, nothing set. Reserved, must be kept at reset value. Delayed conversion mode, turned off, so we don't care. Bit 13, single continuous conversion mode. So that is something that we've talked about a little bit in the notes. So this tells us that bit 0 means single conversion. So we may want to care about that later on. That's all we need to know there, though. Bit 12 is overrun mode. So if we have an overrun, this tells us what happens. An overrun is like we do a conversion and then another conversion happens before we read the results of the first conversion. And so this does mean that we are going to overwrite on overrun. So in the event that we see an overrun, we're going to overwrite that data. Bits 11 and 10, that is a 0, 1 in those 2 bits, and that means that hardware trigger detection on the rising edge. So rising edge is something we might care about. External trigger selection, 9 through 6, is 0, 1, 1, 0. And so 0, 1, 1, 0, if we look at that, it means event 6. And we're probably going to have to look up and see what that means. We'll find that in the manual here. And then we've got data alignment is a 0, so right aligned. Data resolution, in this case bits 4 and 3, is 1, 0. And so that means we're doing 8-bit conversions. And then we've got not data resolution, DFSDM mode configuration, not set, so disabled. Direct memory access configuration, not set, so disabled. And direct memory access enabled, also not set, so disabled. So now we need to look for what those event bits mean. And we need to just look up a little further in the manual to find what the events are that can trigger a conversion here. I think it's up higher. Give me a moment, since I am doing this live, because I'm running out of time to be able to do this video, so just bear with me. There we go. So these are the triggers that can be used, and we're actually looking for the EXT triggers here. So EXT0, and we can see EXT cell 3 to 0 here. And this would be something that I think if I asked this question, I would sort of ask you on the exam and explicitly indicate that this is somewhere you would need to look to find this particular value, because it is hard to find. If we look through these values and we find 0110, we can see that is linked to EXTI line 11. So we might want to remember that event 6 is EXTI line 11, right? So some external interrupt that's connected to the ADC. So let's go back into our registers and let's find the next one that we want to look at, and that is ADC SMPR1. So let's find that and see what that looks like. And we can see that this is effectively SMP plus is do something bit 0, or if we have a 0 here, that means that we're sampling at 2.5 ADC clock cycles. So that's going to be our standard value for that. And then bits 29 through 0 are our channel X sampling time selection. So every 3 bits are telling us for each channel here what is the sampling rate for that particular channel. So let's go ahead and just scan through. Is anything different than 0, 0, 0? So that would be channel 0, channel 1, channel 2, channel 3, channel 4, channel 5, channel 6, channel 7, channel 8, channel 9. And that's what we're seeing. Or sorry, I guess they're labeled a little differently. Or no, they're not. They're good. So that's all the channels values there. And we want to look at this table to see what those values mean. So for all the ones that are 0, 0, 0, that is 2.5 ADC clock cycles. If we see ones that don't say that, here we've got 1, 1, 0 for 5 and 4. So those are at 247.5 ADC clock cycles. So we're setting a lower sampling rate for channels 4 and 5 if those become relevant. So that may make a difference. We'll see. Let's look at ADC SQR1 now and see what that looks like. So SQR1. And this is the ADC regular sequence register. I think this is mentioned in the notes explicitly, that this tells us what channels are being converted and sort of which ones are being converted. So let's first look at the rightmost bits. This is written by software to determine the total number of conversions in a regular channel conversion sequence. So the fact that we've got in bits 0 through 3, the value 0001, that means 2 conversions. And that's going to tell us what we should expect to see in the rest of the register. 5 and 4 are reserved, so we don't care about them. Bits 6 through 10 are the first channel in the regular sequence. And if we read this as binary, that's what it says that means is channels 0 through 18 assigned as the first in the regular conversion sequence. And it's just the channel number in those 5 bits. So this is channel 4. And then if we look at the next set of bits, and I may have miswritten this. This should be over one more. Sorry about that. This should be 101 here. And that should be channel 5 is what we're looking for here. I misplaced those bits. And then the rest of them should be 0 because we see we have 2 conversions, so it's channels 4 and 5. Let's go ahead and circle some of the rest of this information. So we've got voltage range on the Nucleo board. We've got Vmax is 3.3, Vmin is 0.0 volts. And just give me 1 second here. I'm also getting a little bit of a blurriness, so I'm going to try to focus in a little better on the page. Let's go ahead and keep that. That's a little better. So we've got our voltage max, voltage min that we may need later, and we've got our ADC clock frequency. So that's when we say 247.5 ADC clock cycles, that's going to affect what we have here for that 30 megahertz. So then, based on the contents of memory given above, what channels are being converted? So let's look at what we already sort of wrote down. And we see that we do 2 conversions on channels 4 and 5. So that's all we needed for that one is just channels 4 and 5. That's it for that one. We did all the hard work already. What will trigger an analog to digital conversion? Well, we saw that we have this single conversion on an overwrite on overrun. We saw that it was rising edge based for the event. Event 6 was EXTI line 11. So a rising edge on EXTI 11 is what's going to cause a conversion. So that's basically set up so that when some event happens external to the device, we can then trigger that conversion, make it happen. And again, that's just from that CFGR register that we looked at in the manual and figured out that those are what those bits meant. For part C, based on the configuration, what is the resolution of A to D conversions? So our resolution equation is Q equals our Vmax minus Vmin over 2 to the n, where n is the number of bits. So we're just going to plug our values in. We've got 3.3 volt max minus 0 volt min over 2 to the, we found that we're using 8-bit conversions in our CFGR register. So we're doing 2 to the 8th, and that's going to be 3.3 divided by 2 to the 8th. Got to run this through the calculator. 2 to the 8th is 256, I think. And that should be 0.0129 volts as our resolution. So again, that's based on the equation and the fact that we found that it was 8 bits in the configuration register. Moving on to the next part, I'm going to kind of scrunch up the top here so we still have all of our values that we need for the rest of these calculations. And then we'll look at the other problems, so let's just keep that there. Next, it says the ADC has finished converting a sample on one of the channels and triggers an interrupt. The voltmeter reading from the analog source measured 2.15 volts. Fill in the contents of ADC1DR. All reserved bits can be filled in with a 0. So here we really just need to know what the data register looks like. And this is just, it's going to be 12 bits of data, or in this case 8 bits of data, because that's how many we are scanning for. That's what we configured. And we're going to take this voltage reading and convert it into the range of bits that we have for our analog to digital converter. So we're going to take our 2.15, divide it by our maximum voltage value. And we can do this sort of easy way because we've got 3.3 to 0. So our baseline is 0. We don't have to sort of scale down. If this was a positive and a negative voltage range, we'd have to find where this voltage is within that range and sort of what percentage of it is. But in this case, we can just do divided by 3.3 volts. And that's going to give us our percentage of the sort of range that we are working with. So 2.15 divided by 3.3 is going to be about 0.652. And we'll sort of keep that value around. Now that we know where this is in the voltage range, we need to know where this is at in the range of values that we have. And we've got 2 to the 8th minus 1 is our max value, so 255. And we've got 0 as our min value, so we're 0 to 255 here, which means that we're going to multiply this by 255. And that's going to tell us what value we get out of 255. So 0.652 times 255 gives us 166. And so that's what's going to come out of our analog to digital converter. Sorry, my blind cat is trying to walk around here. I'm trying to keep her from knocking stuff over. You get all the bloopers since I'm trying to do these as quickly as I can this week. So we've got 166 as our value. Now we need to be able to put that into a register. So we need to know 166 in hex. And 166 in hex is going to be OXA6. At that point, we're just plugging in that value in binary. So 6 is here. And then A is going to be 0, 1, 0, 1. And then the remaining bits are all 0. And we could zero out the rest of that. And I think that's what it does say to do. So we'll just fill in our zeros. All reserved bits can be filled with zeros. So in this case, because it's an 8-bit value, we can just kind of stop at A6 there. We don't really need to necessarily fill in the rest of it. But since the problem says to, we'll do it. Last question on this part. I know this is a little bit of a long one. Is part E, what is the maximum frequency of input sine waves to the selected channels that will not cause aliasing? So this is a bit of a tricky one. We are going to, of course, maximum frequency that will not cause aliasing should trigger the Nyquist equation. So our sampling rate, our Fs must be greater than or equal to 2 times F max. And so what we're trying to figure out is this F max, and it's going to be less than Fs divided by 2. So that's what we're trying to find, F max less than or equal to Fs divided by 2. So we're trying to figure out what is the maximum sampling rate that we can get on this device, given the parameters that we've set here. So let's look and see what might affect this. We've got our ADC clock frequency, which is 30 megahertz. And we see that this says ADC clock cycles, right? So 247.5 ADC clock cycles. It turns out that the way that that's calculated is we take this and we multiply it by the number of bits that we're doing, and that tells us how many total clock cycles it's going to take us to do this conversion. So we've got our 8 bits times 247.5 clock cycles, or ADC clock cycles per bit. That's going to give us our total number of clock cycles that we're going to take. This is actually the same as some of the equations we've done so far. We've said, 15 cycles, and that 15 cycles is the 2.5 baseline clock cycles times 6 bits. So that's where we've been getting that value from in the previous practice problems. But now we're having you actually calculate it out. So it's 247.5 times the 8 bits that we're converting. And that means it's going to take us 1980 ADC clock cycles total to do all of these bits. And so that's the idea, is it's going to take us a little bit longer. We're sampling a little bit slower, and that's our rate now. So it's taking us 1980 ADC clock cycles to do a conversion. And we've got a rate of 30 megahertz, which is 30 million clock cycles per second. So we're going to take our 30 megahertz, and we're going to divide that by our 1980 clock cycles, and that's going to give us our rate at which we can perform conversion. So this is a little bit confusing because 30 megahertz is cycles per second, and then we're doing some number of cycles to do a conversion. And what this is going to give us is another frequency, but hertz is going to be sort of overloaded here, that we're going to do conversions per second instead of cycles per second in the second hertz number we're going to give here. So let's go ahead and do that. So 30 million divided by 1980 is going to give us 15151.5, and that's our kilohertz value. So that is hertz. So I guess, we'll just leave it as hertz there. So 15.151 kilohertz is what we're looking at, and we can just maybe list that out. So 15, let me divide this by 1,000. Also late, so bear with me. 15.152 kHz. So that's where we're at with a single conversion. We need to keep in mind that we are doing 2 conversions per set. So each of those conversions is going to happen in sequence, and that means that for each of them, it's actually going to be half as fast as our maximum speed. So our sort of rate per sequence is now going to be 15.152 kilohertz divided by 2, because it's going to take us, to convert one channel, we're going to convert channel 4, then channel 5, then channel 4. And so it's going to take us, 1980 clock cycles on one of them, and then 1980 clock cycles on the other one, which means they're going half as fast. So we're going to take that 15.152 divided by 2, and that's going to give us 7.576 kilohertz still. And that is our frequency that we're going to be able to convert these 2 channels at 1980 clock cycles, which is coming from our 247.5 ADC clock cycles and our 30 megahertz. So those are all getting plugged into this. We're multiplying by 8 bits. A lot of this info goes into this last question. And then finally, this is our sampling rate. But we've got to divide it by 2 so we can figure out what our F max is, because that's what we're applying to the regular Nyquist equation. So our F max is going to be less than or equal to 7.576 divided by 2, which is going to be 3.788 kilohertz. So that is the fastest we can sample if we do 2 channels at a time at this slower sampling rate that we've limited the clock to in the parameters. That was a long question, but we are done with the ADC question now.